So we looked at the Taylor polynomial, and I wrote this out on here just so that you could see it. But what we're doing is, instead of doing like a 3rd degree Taylor polynomial or a 4th degree Taylor polynomial, the idea is that if you take that out forever, it will converge to the exact value, if that makes sense. Then it wouldn't be an approximation anymore. It would be exactly perfect. Okay. So where are those going to converge? Do they converge or do they diverge? R is called the radius of convergence. And so what this is going to look like, if you want to draw like a little number line to illustrate this, you have that value C around which you're centered. And so the radius of convergence is how far away from that value you can get before it won't converge anymore. So you can go this distance of R in either direction. So it's basically how far away from where you're centered can you get for it to still converge. Does that make sense? Like how far away can you get? Okay, so that's the radius of convergence. The set, so that's that distance. The set of all values for which the power, it's called a power series when you take it out forever. The set of all those values is called the interval of convergence. So here's the ways that this can turn out. It could converge only at C. So like literally just C and that's it. That's like the only value it would converge at. What's a lot more likely to happen is the second option. It converges for all the values less than R. Like you can get a distance of R away, but no further. Now there's 4 ways that that can kind of turn out. So if you want to, I'm just trying to illustrate the choices for you. If you want to draw out like 4 little number lines here. So you would go a distance of R away from that center. And so you could either keep both of the endpoints, like it will converge at both of those endpoints. It might converge at the first one, but not the second one. So do you see what I'm doing with like the brackets versus parentheses here? Or it might diverge at the first one, but converge at the second one, or it might diverge at both of them. So what you end up having to do is check those endpoints to see if it converges or diverges at each of the endpoints. Which is not hard, it's just like, this lesson is like a lot of work. Like you have to write it all out. Or you could find that the series converges for all values. So like literally everywhere. So like fill in your entire number line. So we're going to determine the radius in the interval of convergence. So you get R, that like how far away from the center can you get? And then that's the radius of convergence. And then to get the interval, you check the endpoint. Now, where are we centered? Most of them are going to be 0. And you can tell by looking at X, like see how this is X minus nothing, like there's nothing added or subtracted in it. Like the majority of the time it's going to be 0. In fact, I only put 1 on here that's not 0. Can you find it on this side where you have like X plus or minus something? Do you see how there's an X minus 2? That one's centered at 2. If you want to think of it like a transformational thing, like moving left 2 or right 2, it's exactly like that. Okay, so that one's centered at 2. All the rest of them are centered at 0, which is usually the way that this goes. But the way that you find your radius of convergence is with the ratio test. So we're going to do the ratio test for each one of these. So let's go ahead and set that up. I know it's a little bit of writing, but you're going to be okay. All right, limit as n goes to infinity. So we're going to plug in n plus 1. And then that goes over the series itself. And then we're going to see what we can cancel out. So limit as n goes to infinity. Let's see. In the numerator, we'll just have an n plus 1 and also an x. Remember, n factorial is n times n minus 1, n minus 2, n minus 3. Or like if you think of it with a number, sometimes it's easier, like 7 times 6 times 5 times 4. Like it's all going to cancel except for the last one. And then same for the x's. So now evaluate the limit. As n goes to infinity, this is just going to keep getting bigger and bigger and bigger and bigger. So this goes to infinity, which means it diverges. And so your radius of convergence is nothing, since we found that it was divergent. And so it's this first situation. We are only convergent at where we're centered, which is 0. So your interval of convergence is just literally c equals 0. That's it. I need an abbreviation for interval of convergence because I don't have to write that for every single problem. Do you guys have something good that we could abbreviate that to? IOC. Can we go with that? Don't write that on the AP exam, but is that okay? I'll accept it. Don't write it on the exam. All right. So we found that that diverged. So the only place it's going to converge is literally where it's centered, which is C. Does that make sense? Okay. Let's try another one. So again, it starts with the ratio test. So limit as n goes to infinity, we're going to plug in n plus 1. So x to the n plus 1 over n plus 1 squared. And then that's all over the series itself. So then we're going to do the reciprocal. So this n squared is going to come up to the top. So it'll be x to the n plus 1 times n squared. And then all this stuff in the middle is what goes on the bottom, but you want to like try to line it up. Like I'm going to put that x to the n first and then the n plus 1 squared. And again, if you want to skip this first step and jump straight there, you can. Like if you're able to flip it in your head, I kind of struggle with that. Like I have to write it down to stay organized, but if you are good with skipping that, then you can. All right, so we can get something to cancel. What's going to cancel out here? Good, these will cancel. We'll just have an x on the top. And actually that's it. We really can't do anything else there. And then you evaluate the limit. So as n goes to infinity, we have an n squared in the numerator. If you were to multiply this out, you would have an n squared in the denominator. When they're the same, you use the coefficients. This coefficient is x. This coefficient is 1. So x over 1 would just be x. So we just end up with absolute value of x. And the ratio test, this converges when this is less than what? The ratio test. 1, less than 1. So we're centered at 0, and we can get a distance of 1 unit away. So let me draw a picture. Our radius of convergence is 1. We're centered at 0, and so we can get up to 1 unit away. So up to +1 or down to -1. Sometimes all they ask you for is r. And if they do, like most of the time it's 1, because this has to be smaller than 1. But if they ask you for the interval of convergence, you have to test these endpoints. Okay, so this is where this ends up being like a lot of work. So let's test them. Let's let x equal the -1. You're going to plug -1 in for x in the original problem. So wherever there's an x, you're going to plug in a -1. So that's going to be sum from 1 to infinity, -1 to the n over n squared. Welcome back to last unit, the test that I just passed back to you today. You have to decide what test you're going to use and does that converge or diverge. So what test would you want to try to use? Good, alternating series test. There's 2 parts to that. What's the first part? Limit's got to equal 0. And it does. What's the second part of the alternating series test? Good, the terms have to keep getting smaller. So 1 over n plus 1 squared has to be smaller than 1 over n squared. Is that also true? Yes, because the bigger denominator is going to be the smaller fraction. And just for good measure, this is starting at 1. So we're going to say converges by alternating series test. Good, so x equals -1 works. You're probably like, wow, this is a lot of work for one problem. You're not wrong. This shows up on the free response part though. And it's worth a lot of points, and you can get them all if you just stay organized and go through each step of it. All right, now we're going to try positive one. So you're going to look back at the original problem and plug in positive 1 for x. Now, if you do that, you get 1 to the n, which would just be 1. So it's 1 over n squared. Again, well, good, p-series. Does it converge or diverge based on being a p-series? Converges. So converges because p-series with p equals 2, which is greater than 1. So now your whole conclusion to the whole thing, our interval of convergence, which we're going to abbreviate IOC, don't do that on the AP exam. Both of these converged, so that means we can keep them both. So -1 to positive. So your radius of convergence is 1, we're centered at 0, and we were able to keep both endpoints, so brackets on both of them. I know that's a lot of work. Let's try one more and then I'll give you a little brain break, okay? All right, so again, it starts with the ratio test. Limit as n goes to infinity. We're going to plug in n plus 1 everywhere we see an n. And then that goes over the series itself. So then we're going to do the reciprocal. So this n is going to come up to the numerator. All this stuff in the middle goes in the denominator, but you want to line them up. So put the x to the n first, and then the n plus 1. And again, if you're comfortable jumping straight there, then. So what is going to cancel? Good, you'll just have an x. And where will it go? Up top. Okay, good. So we'll have limit n goes to infinity, just an x in the numerator times n over. Good. These are both n, or n to the first. Since it's the same, we're going to use the coefficient, which is just x over 1. So again, it just comes out to x. For the ratio test, in order to converge, that has to be smaller than 1. Again, most of the time it comes out to 1 for that reason. If you're like, hey, what's an example of one that doesn't? I have one on here later that doesn't come out to 1. It's just commonly 1, like obviously, okay? So our radius of convergence is 1. And again, sometimes that's all they ask you for. That's all they ask you for, you're finished. Like that R value is 1. But we are centered at 0. And we can get 1 unit away in each direction. And so we're going to test those endpoints to see if it converges or diverges, to see if we can include them. So let's let x equal -1. You're going to look back at the original problem and plug in -1 for x. And I know this is tricky because there's an x and there's an n, and that's tough to keep them separated. But n is like your number of terms, like first term, second term, third term. X is just a variable. So again, you would want to do alternating series tests for that. Limit as n goes to infinity for that. Will that come out to be 0? Yes. Good. And then the terms are going to keep getting smaller. So 1 over n plus 1 is going to be smaller than 1 over n for n's bigger than 1. And so this converges by alternating series tests. And then we're going to let x equal +1, which means you're going to plug 1 in for x in the original problem. What would that give you if we just plug in +1? 1 over n, good. That's, you can say, now I usually just go with p series because that's what I'm used to writing. But yeah, if you say the harmonic series, that's fine. So diverges because p series Perfect. You guys rocked. How much you guys remembered, and we even had spring break. You guys are awesome. Or you can say diverges because harmonic series. That's fine too. You guys wrote that on your test, and that was awesome. So our interval of convergence is, yeah, we're gonna have a bracket on the negative one and a parenthesis on the positive.